Good morning, guys. All right. Yesterday we talked about vector as a displacement vector, and the thing that you saw about displacement vector, it is the same fact about vector in general. In other words, adding vector, subtracting vector, scalar multiplying, and so on. And you can apply this in different actually spheres. And I showed you actually some of the interesting parts that we are going to deal with mechanics and so on. Still, we will see with electricity and magnetism how it works when we start the topic. So we move forward and let us see another vector operation. That is still the vector multiplication. And the second kind of vector multiplying is multiplying vector by a vector. The first one was multiplying vector by a scalar. And that means you get another vector, and that vector is going to be in the same direction as the original vector. If you multiply it by a positive number, it will be in the opposite direction if you are multiplying it by negative scalar. And the vector is going to be larger if the absolute value, or longer than the original, if the absolute value is greater than 1, and it will be less in magnitude when it is actually less than absolute value is between 0 and 1. All right. So now the second type of multiplication is multiplying vector by vector. And this time you'll get scalar. And there is another third type of multiplication is multiplying a vector by a vector. You get the third vector, which is orthogonal to both vectors, that is cross product. So here is the dot product of two vectors, or sometimes we call it scalar product. Vector u dotted with vector v is the norm of vector u times the norm of vector v multiplied by the cosine of the angle between them. Actually, we have the proof for this using the cosine law of finding the lengths of a triangle, of the sides of a triangle. And you have done this one last quarter, so I'm not going to go through the proof. So in this case, it's piecewise defined. When both u and v have a magnitude different from 0, we use this one. If either u or v is 0, no matter what angle is going to be, you are going to have 0 dot product. Theta is the angle between the two vectors, and always we are expecting theta to be between 0 and pi. And when it is really in a component form, the dot product of the two is multiplying each component and add them, and you'll get the actually the result. So without really going further, why not you find the dot product of these two vectors given in a component form? Go ahead and do it quickly and write your answer on chat. Okay, so the answer is 3, and that is quick. All right. Now, the next thing that we need to know is actually how do we determine? We know that the dot product between U and V is the norm of U uh, multiplied by the norm of V multiplied by the cosine of theta. And then now, yeah, we can find the magnitude of U, the magnitude of V. How about angle theta? How do we really find it? Well, what we can do is, if it is given in a component, and I will solve for theta, that is what we have. And now to find the angle theta.
Oh, Professor,
Yes, sir.
can you let Tyler in
Uh,
to the
say
meeting?
what?
Tyler's in the meeting.
Waiting room? Oh,
Yeah.
thank you.
Yes.
Okay. That's great. Thank you for reminding me, actually. On that.
Of course.
Okay. That is great. Okay. And then we have this. Then to find actually theta, take the arc cosine of both sides. And this is really the formula that we need. And now, as you know, since we have this theta, and look, you have this norm, it is a scalar, this is a norm, that is a scalar. And what we need to do is actually this angle, theta, we said, is between 0 and pi. So what are the possibilities of being theta? And actually it has a implication as well. If actually, all right, then what actually, yeah, moving it back and forth, it is bad. I have to pay attention to the screen. Thank you. All right. So what we have to really take into account is, well, when are we going to get 0? Well, that means the cosine of value is going to be 0. Therefore, cosine is going to be 0 actually when theta is pi over 2. All right? If vector u, that means, and vector v are orthogonal, from here we can say actually the dot product is going to be 0. Then now this cosine, as you know, it is between the first and second quadrant here, obtuse. The total is 180. So cosine is going to be positive here, and here negative. That means if actually the dot product u dot v is positive, that means theta is what? Between 0 and pi over 2, and strictly like this. All right. Actually 0 we can, well, if it is 0 it will be also so strict inequality. Then if u dot v is actually less than 0, that means this cosine value is affecting it, because norm of u is a positive number, norm of b is a positive number. Length cannot be negative, so the angle is really influencing it. Therefore, that means what? The two vectors are forming between actually an obtuse angle, which is between pi over 2 and pi. That is really what we need to know. And remember, dot product of 90 degree is 0. Then what can we say? The unit vector I and j, they are forming 90 degrees. Their dot product has to be 0. The dot product of I and k, and for that matter, j and k, all these are going to be what? 0. All right. Then now, what I am going to ask you is, why not you find the angle between these two vectors? The first vector is a unit vector, which is in the y direction, 0, 1, and the second vector is -1 radical of -3. So find the angle between these two vectors. Okay, this is not really bad. You have the dot product of the two. Actually, negative radical of 3 will get negative radical of 3, and the norm actually is going to be 1, and this one is also actually 2. 1 times 2 is 2. So negative radical of 3 over 2. That means radical of 3 over 2 in the first quadrant is pi over 6. Therefore, actually, the angle is going to be 5 pi over 6. In other words, if you have the angle, as you know, when it is theta is pi over 6, this terminal point is going to be radical of 3 over 2 and 1/2. And then if you go over here, this is also pi over 6, the reference angle, but the cosine is negative radical of 3 over 2 and 1/2. And this angle from pi you subtract, actually pi over 6, 5 pi over 6 from your trigonometry. Make sense, guys? Okay, so the other thing that you learn is property of dot product, and let us really review that. When you are taking the dot product of two vectors, commutativity is applied. I mean, it holds true, because look, the norm of the first vector times the norm of the second vector, positive number, and times the angle between them. So the angle will not really change between u dot v and v dot u. Therefore, the commutativity holds true. Second, you can apply distributive law of actually vector dot product over addition. So you can add these two vectors and dot it, or you can dot this vector u with v and dot u with w, and add them, still you get the same answer. Actually, we can prove all this very simple by using the component of vectors. And the third property is, when you have a scalar and take the dot product, either you can multiply the first vector with that scalar and dot it, or you can actually multiply the second vector and dot it with the first one, still get the answer, the same answer. Third one is, when you are dotting a vector with itself, that means the angle between the two parallel vectors is 0. Cosine of 0 is, as you know, 1. That means what? The norm of the first vector times the norm of the second vector. In other words, look, u v dot v is, by definition, the norm of v dotted with, times the norm of v again, times the cosine of theta. So, because v and v, they are parallel, the angle between them is 0. Therefore, cosine of 0. And cosine of 0 is 1. Therefore, you end up getting norm of v times norm of v. And this is actually, the norm is squared. That is what it means. So this is really simple and quick. That's why I intended to show you. Okay, if we know this much about property, one of the application of dot product is work done by a constant force. As you know, work in mechanics, mechanical work, which is scalar, is force multiplied by the distance. And that is the times. If the force is acting on the direction of the movement, if this is an object, and if I'm pushing it parallel to the direction, then this is force times distance. Force is a vector quantity, and the displacement is also a vector quantity. Now, on the other hand, if you have this distance or displacement d, and the force is acting like this one, you are maybe pulling, and they are forming angle theta like this one. Then what happens? The force that you are going to really deal with is going to be the projection of this one. Okay, if you have F, the actual work that you are going to do is F times cosine of theta is going to be the adjacent this one, because cos theta is this adjacent V multiplied divided by F. Therefore, F is going to be therefore F cosine of theta and multiplied by D. Then what happens? Work equals force, which is the magnitude of that force that we are going to do, and the displacement is also force, and the angle cosine theta. Aha, when we see this, what does that mean? This is actually the dot product of two vectors, F dotted with D equals W, work. And that is what you have to really remember. So the formula for work is work is equal to force dotted with D, which is the norm of the force, multiplied by the length of the distance, multiplied by the cosine of the angle between them. All right. Then now what I'm going to ask you to do is, please do this problem. Very simple and quick. Find the work needed to move an object 3 meters if 6 Newton force is applied to an object at an angle of pi over 6 with a direction of motion. In other words, the angle pi over 6 is the angle between the acting force and the direction motion. So again, I screwed up. All right, thank you. Keep reminding me, don't be hesitant. Yeah. Okay, well, this is not really that bad. 3 times 6, which is really given, and the cosine of pi over 6. And cosine of pi over 6 is radical of 3. So what you are going to do is, really, you have 9 square root of 3 Newton meter, or it is called joule. Or what you are going to do is, in component form, if you want, 3 meters horizontal. In the x direction, it has a component of 3. In the y direction, it has a component of 0. And that actually the force, it is forming an angle of pi over 6. The x component will be 6 times cosine of in a polar form, and the y is this one. And in both directions, it is, you will get what? 9 square root of 3 joule. Okay. Now, I'm going to give you another example, and here it is. A constant force with vector representation of F, which is having I plus 2j moves an object along a straight line from point 24 to the point 57. Find the work done in foot-pound if the force is measured in pound and the distance is measured in feet. Please do that. Number 20. Is it readable, guys? Okay, great. So what you need to do is you need two vectors, the displacement vector and the force vector. So you are using the dot product of two vectors. So we are going to really apply dot product component by component in this case in order to get that work. Therefore, if you are given two vectors, 2 points, the position vector is going to be from 5 you subtract 2 and from 7 you subtract 4, that is 3 3. And then now what you get is you multiply that by 1j. Is it clear? And you get 9 foot-pound. Do you guys get that, or do you want me to work it through? Okay, I'm waiting. Is that okay, or do you want me to show you? Understood? Okay, good. Then let us move on. Then now, actually the next one is find the angle between between vector in 3D space and coordinate axis. That means with the z coordinate with respect to the axis, with respect to x-axis and y-axis, how the angle cosine is really formed. If you have this vector, which is really pointing this way. Okay. All right, let me switch. Okay, suppose I have this coordinate system, x, y, and z. And now I'm going to have a vector like this. So now we want to find the direction of this vector in reference to the 3 axes. So we call it the direction of cosine. And that will be given this form. Let me switch the camera and show you the work displayed. Okay, so it will be actually finding the angle between unit vector is going to be u over the norm of u, and it has this component. So any unit vector can be expressed in terms of its direction cosine, alpha, beta, and gamma respectively, alpha in the x direction, beta in y, and gamma z respectively. Since cosine alpha is the dot product of u and I divided by u, as you know, the dot product of unit length and this one is going to be give you the x component only. So u1 over u, and likewise cosine beta, u dotted with j divided by the norm, and that is actually u sub 2 over u, and likewise u dotted with k, you get only the k component, x and y component will be vanished, so u sub 3 over u. Therefore, the direction cosine is going to be the x component of that unit vector over the magnitude of that vector. I mean, the vector u, not necessarily unit vector, and the second component, and let me put comma here, sorry, and cosine alpha, cosine beta, cosine gamma, they are going to really form of this form. So that is really what the cosine of the angle is going to be. And if you really multiply, what happens? Obviously, cosine squared of alpha, cosine squared of beta plus cosine squared of gamma, if you do it, the x component of u over the magnitude of u plus the y component of u over the magnitude of u, and the z component of u over the magnitude of u, and it is squared, add them, and then actually you will get 1. So now what I'm going to ask you is, for example, if I give you a vector which has a direction of, sorry, again, you cannot see it, but now I hope you can read it. You are given a vector u, which has a component 2, -1, and -2. I want to find the direction vector, the cosine of alpha, gamma, and beta and gamma, respectively, in the x direction, y direction, and so on, the direction. What will be? So this is really quick. First of all, we have to find the magnitude. 2 squared is 4, -1 squared is 1, and -2 squared is 4. 4 plus 4 is 8, plus 1, 9. Square root of 9 is 3. We're done. Then now what we are going to have is, 2 over 3, -1 over 3, and -2 over 3. That is a cosine alpha. And then if you want actually to get alpha or beta and so on, well, cosine inverse of 2 over 3 will give you what is the angle on the x with the x-axis, and cosine inverse of -1 over 3, that is the angle between the vector and the y-axis, and cosine inverse of -2 over 3 is the angle between the vector and the z-axis. So the directional cosine apply also to two d vectors, two-dimensional. Then what we are going to do is cosine alpha, cosine beta. Well, actually, if the angle it is in 2D, x and y coordinate are forming actually 90 degrees. In other words, if you are going to have this vector, this is the y direction and x direction, and if I have this vector, and this is really forming, let's say, alpha. And then now, this is the angle, and this is going to be angle beta, and this is really 90 degree. By alternate interior angle, this is also beta. Therefore, beta can be expressed in terms of eta alpha. From pi over 2, you subtract alpha, that is also beta. So actually, if you have cosine of alpha is the x component with the x-axis, and cosine of pi over 2 minus alpha will be with the y-axis that is going to really create. So you have cosine of alpha or cosine of pi over 2 minus alpha is going to give you cosine alpha, sin alpha, since alpha and beta are complementary angles. All right, the next thing that we are going to really work with is projection. And one of the things that I showed you is actually when we do a work, the component of vector B along vector A is what? Actually, from what we defined. Look, I'm going to give you pictorial representation so you can have a clear idea. Suppose, just like when we define the work. All right. Let me have this vector A and this vector B, not necessarily horizontal. This is a vector A and this is a vector B. And now I'm going to project this vector B on A. So what happened is, it is really this. So how do you find? If this is theta, then actually the component, let us call it actually B1. B1 equals norm of B multiplied by cosine of theta. All right. And actually this one, let me call it actually B1. It is a component of vector B on vector A. And that is what we call it is actually, the norm of vector B multiplied by cosine of theta. Okay, well now, from unknown to the known, I want to really take it. If I multiply this quantity by 1, this expression will not be changed. So what I'm going to do is, then can I write this one as norm of A multiplied by norm of B cosine of theta divided by norm of A. If you see, norm of A over norm of A is 1, and this is the original that I get. Well, if you see this one, actually it is by definition A dot B divided by norm of A. So the projection, the scalar projection, which we call it component of B onto A is the dot product of the two vectors divided by the norm of the vector that you are going to project on. All right. So now if I have vector B, a component, vertical component B2, then how do I get B2? Well, remember, vector B is really represented by B1 and B2, we said. And actually this vector B, by geometrical form of vector addition, okay, B1 plus B2 will give me vector B. Then actually, how do I get vector B2? Well, from the vector B, I subtract vector B1. So the orthogonal, because it is forming a 90 degree, orthogonal of B onto A is going to be actually from vector B, I am going to subtract B1, which is this. So in other words, the orthogonal is from B, you subtract component of B onto A. That is the orthogonal of B onto A. So these are actually things that we need to know. Okay, so here it is, what I explained. So the component is going to be this. And if you want to make it, and by the way, this is going to be a scalar. If you want to make it a vector projection, we call it, instead of component, the vector projection of B onto A. That means cosine of B, the norm of B multiplied by cosine of the angle multiplied by unit vector, because in the direction of A, you have to have a unit vector. When you multiply by the unit vector, this value will not change because the magnitude of unit vector is 1. So how do I get unit vector? Unit vector is any vector A divided by its norm A. And that will give me, since I have here A, and the magnitude of this is going to be A over norm of A, that is why A dot B over norm of A squared multiplied by A. That is the projection, and the orthogonal is going to be vector B minus the projection of A on B. And that is what you have done. Okay, let's do example. Okay, can you find both the component, the projection, and the orthogonal vector for this two-dimensional vector? B has component of 3, 2, and A has component of 2, 1. And I want to find the component of B on A, that is this, and what will be actually the projection of B on A, and what will be the orthogonal. Go ahead. Okay, let me really draw it roughly so I can have a clear idea. This B has a component of 3, 2, and vector A has a component of 2, 1. And let me call this one A and this is B. So you can see it. I mean, the picture is really representative. I didn't draw it perfectly. It doesn't matter. As long as you have a reference, that's fine. And then now what I'm going to do is, let us find the component. Component of B on A. And that is the dot product of AB over norm of A. That is what I need to do. And that is 3, 2 and 2, 1 divided by the magnitude of this, actually square root of 2 squared plus 1 squared. All right, and this will give me 2 times 3 is 6 and 2 over square root of 5. All right, and as you know, this is actually 8 over square root of 5. And as you know, component is a scalar, and I have that scalar. And now what will be the projection? It is A dot B multiplied by, divided by the norm of A, and that is squared, and multiplied by vector A. All right, And that is going to be, this one I have already 8, and the norm of A is square root of 5, therefore it is going to be 5, and vector A has a component to 1. So our answer is 16 over 5 and 8 over 5. And that's actually what is the projection. And now, what will be the orthogonal? Orthogonal of B on A. That means from vector B, you subtract projection of B onto A. And vector B has a component of 3, 2, and you are subtracting 16 over 5 and 8 over 5. And then now this will give us from 15, because 3 times 5 is 15, you subtract 16, you'll get -1. And then from 10, you subtract 8, you get 2. And that is what we have. So in other words, this vector has a component. This component is for this one, and this component is for this. That is what you are really getting. Is it clear, guys? All right, now let me go and give you a little bit challenging problem. It's not really that bad, but we can really do it without going to the next step. That means vector cross product. Now this time, I'm going to give you 3-dimensional vector. Here it is. You have vector U, which is actually with a component form -1, 4, 6, and the vector V has 3, 2, and -4. And I want you to find all possible vectors W that are orthogonal to both U and V. Can you find that? Okay, so here is actually what I'm asking you to find. You have two vectors. Vector U, -1, 4, 6, and vector V has a component 3, 2, -4. And I want to find vector W such that vector W is orthogonal to vector U and vector W is orthogonal to vector V as well. So how do you approach to solve this problem?
Probably take the cross product u and b and then multiply it by arbitrary real number constant.
Very good, that's it. But unfortunately, I didn't learn actually cross product. Let us assume that is out of the option. Now, can we use the knowledge of dot product and find it? Yes, you are absolutely right. And that is actually quicker than that we can written. Than the other alternative we have. So another alternative, what do you do? Well, do I know the component of vector W? I don't know, yes? So can I assume it is X, Y, and Z? Is that okay, guys? As a position vector, it will be somewhere, it has a component X, Y, and Z. That is fine, yes?
Yeah.
And then now we know that this vector W is orthogonal to U. That means what? Vector W can be dotted with U, and that dot product is going to be 0. Make sense? And likewise, at the same time, this vector is going to be orthogonal with vector V as well. If that is the case, this vector dot product with V is going to be also 0. And by the way, this one is the alternative technique that we are going to really work, and probably it will give us more options. And now let us take the dot product of these two vectors, W and U. This is actually -1 times X is -X, and 4 times Y is 4Y, and 6 times Z is 6Z equals 0. And likewise, when we dotted with V, 3X plus 2Y minus 4Z is equal to 0. So this gives us actually three unknowns, and 2 equations. So we have a degree of freedom of 1, and you know how to solve system. Then this time, what do I do? Well, I can make X any number. Let X equals some scalar T. If that is the case, what happened? 4Y plus 6Z equals T. And 2Y minus 4Z equals 3T as well. Then this time, T is scalar, as I said. I can solve for X and Y. Well, now what we need to do is, let us solve for Z by getting rid of really Y. I can do that. So how can I get rid of Y? Well, if I multiply the bottom by 2, negative, then I will have this equation, 4Y plus 6Z equals T, and the negative 2Y plus 8Z equals negative 6T. By the way, this is T.
That should be a -4Y on the bottom too.
Yeah, -4Y. Otherwise, the purpose is really bad. It's not really accomplished. Okay. And now, by the way, I made also one error here. This is -3. Am I right? This is supposed to be -3. And this is +3. Is that right? Because I moved this to the other side, so it is -3. So I have here, this is really gone. And then now, when I am adding all this, I have 14z equals 70. So z equals 1/2 of t. All right. Then if I have that, I mean, if z is really calculated, I can use the equation 4y plus 6 times z equals t, and this will lead me to 4y and plus 6 times 1/2t equals t. So 4y equals t minus 3t, because this is 3t. 6 times 1/2 t is 3t. And then this will give me 4y equals -2t, y equals -1/2 t. Then now what do I have? X is equal to t, y equals -1/2 t, and z equals +1/2 t. So my vector w, you can really factor t, that is a scalar, as you see, and I have 1, -1/2, and 1/2. This is one of them. And when t is 1, for example, if t is equal to 1, I will have vector w is going to be 1, -1/2, and 1/2. And if t is equal to 2, if I want to get actually integral, then I have 2, -1, and 1. And by making actuality, so I get infinitely many orthogonal vectors. Actually, if you take the dot product of that, what you are going to get is really you get a single vector, and that vector you can multiply by a scalar, and you will get similar of like this. So you can check this one by using what? The cross product, which we didn't touch it, but using also actually dot product by solving, because since it is orthogonal to both vectors simultaneously, so we can have two equations. And when you have two equations, we end up with 3 unknowns and 2 equations. We have 1 degree of freedom. And then by setting that parameter with that degree of freedom, we have this many choices. By the way, is this vector or this vector orthogonal indeed to this one? Yeah, we can check it. And that is actually if I dotted w to -1 and 1 with vector v, which is let's say u, -1, 4, and 6. If I get 0, that is really fine. Otherwise, I am in deep trouble. That means -2, and this is will give me -4, -4, and 1 times 6 is +6, and this is indeed 0. Is it clear, guys?
Yes.
All right. So now let me make it a little bit even bad. Now, using the same technique, I want to come up with this kind of problem, because we are going to encounter this kind of problem in the future. That's why I'm giving you this. Let vector u have a component, has a component 1, -4, and 2. Find all possible vector v which is orthogonal to you. In other words, you have one vector, 3D, this one, and I want to find another vector which is orthogonal to it in 3D. Can you find that? This time, yeah, if you want, you can use this cross product again, but it will be in terms of x and y, and still you can deal. But can you use similar techniques? Given this vector, find the orthogonal. Let's start with vector v, which has a component x, y, z. We don't know it.
Could we take another vector that is parallel to you but in the opposite direction and then do the same?
Yeah, you can do the same. Yeah. What do you mean in opposite direction?
I guess it doesn't even have to be in the opposite direction, but any vector parallel to you will also have a v that is perpendicular to you if we use the dot product.
Okay. Yeah. If you take another vector, for example, you have this vector. Let me draw it. And the parallel vector is this one. And the parallel vector is a scalar multiple of the other one, yes?
Mm-hmm.
And then now, if you take the dot product of these two parallel vectors, what do you get? I mean, the angle between them is really 0, and you'll get a number. Actually, cosine of 0 is 1. Therefore, what you are going to get the magnitude of this times the magnitude of this one multiplied by the cosine of the angle between them. That is what it's going to give you. And twice of these two lengths. And that doesn't help. But can we find vector v, actually, which has a component of x, y, and z, just like what we did, yes? Then these two vectors, if they are orthogonal, then what happens? The dot product of the first vector with the second vector has to give us what? 0. Make sense, guys? So far? If two vectors are orthogonal, their dot product is going to be 0. Then as a result, what do I have? Well, x minus 4y plus 2z is going to be 0. Yeah, we are talking about linear algebra this. So what is really happening? You have one equation and two unknowns. That means what? You have 2 degrees of freedoms. So you can pick x and y or y and z arbitrarily points, independent of each choice. Then you can solve for x. And now let us assume let y equals, let's say, p, and let z equals s. Then what do I have? X minus 4p plus 2s is equal to 0. Then what is s? X is 40 minus 2s. What about, I need x. X is this in terms of s and t. What about y? Y is really t. And what about z? Z is simply s. Okay, well, can I express this one in terms of x is expressed in terms of s and t? How about y in terms of s and t? I can do that. Well, then x is equal to, I will have 4t minus 2s, and y equals, I have t plus 0s, and z is actually 0 t plus s. And remember, these are vector components. I have x, y, and z. This, if we say two vectors are equal, this vector equal to this one, if each components are the same, that is what we defined earlier. Then that means what? 4, 1, 0, t plus negative 2, 0, 1, s. So this will be actually a vector which is going to be orthogonal to this vector. And you can pick t and s in any way you want. For example, when t is equal to 2 and s is equal to 3, I might have x, y, and z as a vector. Well, 4, 1, 0 multiplied by 2 plus negative 2, 0, and 1 multiplied by 3. And as a result, what do I have? X, y, z, this vector. 2 times 4 is 8. 2 times 3 times negative 2 is negative 6, and that will give me 2. And then 2 times 1 is 2, and 0 times 3 is 0. That means I have 2. And then this is 0, and this is 3. And this is one of the vectors. And if you want to check, 1, negative 4, 2, dotted with 2, 2, 3. Well, it's better give me 0. That is 2, negative 8, and 3 times 2 is 6, and that is 0. So this is really how you can get those things. All right. Wow. We really went over time. I'm sorry, guys. Please remind me in the future. I'm missing the other class as well. We will continue this one tomorrow. Thank you for your attention. I hope you get something out of it that you are not familiar with in previous classes when you learn. Okay? All right.
Thanks.